So let's go over this exceeds standards part of the rubric. Anybody want to read that for me? What it says under 4. Ratil, read the first and second checkbox.
Fulfills all requirements for a 3 and uses mathematical representations to model/demonstrate the relationships between the frequency, wavelength, and speed of waves.
Good. And it says, for example, include calculations, which means show your work, for the frequency of various colors of light or types of EM waves, using the formula V equals F lambda, and apply those values to a model. So this is just taking math skills that you already have from 8th grade math and applying them to something a little more complex that's related to light. That actually comes directly out of the high school standards that they would use in your physics class. So let's start with that equation. This will only take us a second to work this out. So if we start with V equals F times lambda, first thing we always do, define what these variables are. What do we think that V is? Somebody said velocity. What velocity? Shane?
Velocity of a wave.
Velocity of a wave. So if we're talking about an electromagnetic wave like visible light, what would that speed be, Gabby? Speed of light. Exactly. So V equals our velocity, which for this example would be the speed of light, which is on a poster over there on the cabinet. It tells you exactly what it is. But if we approximate it, it's 3.0 times 10 to the 8th meters per second. You should all be masters of scientific notation by now. What do we think F is? Gavin, what's F? We're talking about light waves. Paige? The frequency. Exactly, the frequency. The frequency. What are our units for frequency? Tim?
Hertz.
Hertz. Hertz, which means waves. Waves per what, Tim? Do you remember?
Waves per second.
Exactly right, waves per second. Good. And then this funny Greek letter, lambda, like a baby lamb with da on the end, lambda. Lambda represents what, guys? We covered it several weeks ago. Paige? The wavelength, exactly right, the wavelength. Now, for our wavelengths of visible light, we have most of those in nanometers, but we need everything to be in meters, seconds, and waves. All of our units need to be the same before we can do calculations. So, if we start with blue light. Blue light has a wavelength of, depending on how blue, like how purple or how green that blue is, I'm going to move this up, wavelength of approximately 475 nanometers. 1 nanometer equals 10 to the negative 9th meters. So 1/1,000,000th of a meter. Is that right? 1/1,000,000,000th of a meter. 1/1,000,000,000th of a meter. So that means that 475 nanometers equals 475 times 10 to the negative 9th meters. But is that scientific notation? No, V says it's not scientific notation. V, how do I make it be scientific notation? I need to move the decimal 2 to the left to get 4.75, right? We need a number that's less than 10. 4.75 times 10 to the new exponent. What's our new exponent since we move the decimal 2 to the left? 10 to the negative 11. So we made this number smaller, and we made it to a smaller power because it's negative. So that would be like we moved the decimal 4 places. So when we move the decimal to the left, and we're making it equal, power moves the other way. So these are equal. 475 times 10 to the negative 9 4.75 times 10 to the negative 7. We can figure that out because we can write the number of zeros, but I'm not going to go through that with you guys right now. So if this 475 times 10 to the negative 7 meters, this is our wavelength. We have our velocity up here. So we have v, we have lambda, and we're going to calculate f. So if we're starting with the equation v equals f times lambda, how do we get f by itself? How do we isolate f? Shane?
You divide lambda from both sides.
Divide both sides by lambda. Exactly. This is multiplication. This means f times lambda. So we're going to use the inverse operation. We're going to divide, and we end up with v over lambda equals f, which is the same as saying f equals v over lambda. Then we fill in our values for v and lambda. 3.0 times 10 to the 8th meters per second is the speed of light. Our wavelength, 4.75 times 10 to the negative 7 meters per wave. And if you can do that problem, you end up with the frequency of the wave. Any questions on what we've done so far? Okay, that should get you close enough that you can do the other bit on your own and let me know if you have questions.